Hey, this is Leach with Simpson Math, and in this video, we're going to be taking a look at composite functions. So let's get started by just reviewing function notation. So this says let f of x equal 3x. So I have just a simple linear function, 3 times x. And if I wanted to evaluate the function at 2, so that would be f of 2. Notice what changes between f of x and f of 2. Well, the x is now 2, so I'm going to do the same thing on the other side of the equation. The x is now 2, so this is 3 times 2. It's essentially saying just substitute in, plug in 2 for x. So what if we saw, instead of f of x being f of 2, we said, well, what if it's f of x minus 5? Well, we saw this in our function review video, so let's just do that. So it's going to be 3 times x plus 5. So instead of writing an x in its place, I'm going to write x plus 5 parentheses, which we can then distribute, and we end up with 3x plus 15. So that doesn't seem foreign to us. We've done that before. So I'm going to introduce to you a new notation. So this time, I'm going to say, well, let's actually give x minus 5 a name. I just realized I messed that up. These should be negatives. There we go. Because you freaked out about that. Sorry. The signs don't just randomly change. That should also be a negative, just like this was, x minus 5. Sorry, I got plus in my head. So we have g of x is x minus 5. So I'm just going to stick a name on that x minus 5. So if I do that, let's evaluate f of, I'm going to color code, and I'm going to say g of x. So notice this time, instead of me writing an x minus 5 inside the function, I'm just going to write g of x inside the function. So, well, these two things should eventually be the same thing. So let's take a look. So this is equal to 3 times, well, I'm not going to write g of x right here because that's function notation. I don't want to mix function notation and just multiplying this regular kind of like algebra manipulation. So what does g of x equal? Well, g of x equals x minus 5, which should feel familiar because just a second ago we said that that was 3x minus 15 with the correct signs. So this, what we just did, is a brand new notation called composite notation, or it's a composite function. I am composing. You know how we call a composer someone who like writes music because they compose, they create, they're putting all these things together, all these pieces together. This is what's happening. I'm composing. I'm putting this function inside of the f function. So just to be clear, order matters. I am leaving a little bit of a space because I'm going to put something in between there. But let's evaluate g of, and I'm going to do the parentheses just a little bit bigger, g of f of x. So here I have the f function inside of the g function. This would be just like saying g of 3x. All right, so if I would have said to be g of 3, oh, that's a 3, g of 3x is that same idea. I'm going to take the 3x and put it inside. So g of f of x, so what's my g function? Well, it's just x minus 5, so it's going to be whatever x is minus 5. And then what's the f function? That's the 3x. So it's 3x then minus 5. There's not much math to do there, actually, like none at all, but I'll just drop the parentheses, and so that's 3x minus 5. I want you to notice that these two things are not equal to each other. This f of g of x, and notice how I'm reading this. I'm reading this as f of g of x. When you get to those parentheses, we're kind of reading those as ofs. F of g of x. Its full name, it's the function f evaluated by g of x, and that of x, or the function g, the function f evaluated by the function g, which is evaluated at x. That's sort of all those things. But so these two things are not equal to each other. They might feel a little bit familiar because they're the same numbers, but that order does matter. Let me show you one more notation to go with this. I'm giving myself a little bit more room because I can. And it's using the composite operator. So you know how I was saying of, this looks like I just wrote fog, F-O-G, but that might have done that a little bit too big. This is just a small open circle. You know how we have adding, subtracting, multiplying, dividing, and I can do all four of those things with functions. I can say f of x plus g of x, and you can even call this f plus g of x is another way to simplify that. But now we're not saying plus. This is a brand new operator. This is the composition or composite operator. So what this means, so it's f of g of x. This is the same thing as saying f of g of x. So the same thing as saying f of g of x. Whichever one is second after this open circle is the one that is inside the function. So this is that same thing right there. So that does equal 3 times x minus 5, which is the 3x minus 15. There's a similar thing that is g of f of x. Notice I read it the same way. You could also read it g compose f of x. But g of f of x, which is the same thing as g of f of x, which is what we saw just above. So it's a 3x minus 5. So these are two different notations to say the same thing. I usually like this notation because this is visually a little bit clearer that I have one function inside of the other. So conceptually, this helps me understand. This notation with this composition symbol is a little bit more mathematical because it helps us understand that this is actually an operator, just like adding, subtracting, multiplying, dividing. And then, therefore, in higher levels of mathematics, that matters with things. So don't stress about that. So we have two different notations. They mean the same thing. All right, so let's take a look at this example. So f and g again, but these are different f's and g's. So we have f of x is 5x plus 2, and g of x is 3x minus 4. Okay, so I have 3 on screen for you to do. I would like you to actually try to do these first 2 on your own. So just basically a repeat of what we just did. Try those on your own. All right, let's go over them. And as I do this, as I work through this, I'm going to color code as I can. So we're going to have my f function is that blue one, and you swap to my blue. There we go. So this is going to be 5 times, and I get to my x, and I'm going to put a parentheses, plus 2. So my big parentheses, that's for my g function to go in. So I am plugging in the g function everywhere I see an x. So let's plug in the g function, 3x minus 4. I'm going to write this one more time, but I'm not a fan of this. This is what we saw during the function notation thing. This is saying f of 3x minus 4. All right, just in case you're a little confused about what just happened, g of x is 3x minus 4. So what if I didn't write g of x, but what if I wrote it as 3x minus 4? So that means wherever you see an x, I'm going to write 3x minus 4, and that's what we just did here. Now, I'm not wanting to really do this too much anymore because, I'm not wanting right now to mix the function notation with the like algebra part. That messes up some students. I'm trying to keep those things separate. But that is what we're doing. It is going inside. So now that we have that, we can then simplify this. So let's, crazy things happening. So now let's distribute. So 5 times 3x is 15x. 5 times negative 4 is negative 20. And that plus 2 is still there. It does not get distributed. and then we add like terms, and so that's a 15x minus 18. All right, so then this g of f of x is just the other way around. So this time it's equal to, and it's going to be my g first. So 3 times minus 4. But instead of x, I'm going to put the f function, 5x plus 2. And then let's distribute. So we're going to have 15x plus 6 minus 4 just hanging out there. And we end up with 15x plus 2. So again, these two things do not equal each other. They kind of feel familiar, but they are different. All right, just for practice real fast, which of these two is f of g of x, and which of these two is g of f of x? Well, this one is the f of g of x, this first one, and this one is the g of f of x. They read that same way, left to right. Whichever one's the second one is the one that's inside the function. So that's that. All right, so we have two more, but this time we are going to be evaluating them. I'm going to do C for you, and then I'm going to want you to try to have you do D on your own. So there are two ways to go about doing this. Way one is considering that I just figured out what f of g of x is. F of g of x is 15x minus 13. 15x minus 18. So I don't have to go through all this math again. I just know that that's what that equals. So I'm going to do just that. I know that f of g of x, I'm just going to rewrite it, is 15x minus 18. Make that be clear of 15. So then I'm going to evaluate, instead of an x, a 3. So f of g of 3. So I'm going to replace the x with 3, and I end up with 45 minus 18, which is 27. So that means that f of g of 3, double close parentheses, is 27. So if I'm given, and I'm going to move this over here because I want the room. So if I'm given, if I'm tasked to evaluate, and I already have this simplified, well then why make my life harder? I can just evaluate and plug it in. The other is, especially if I had not done this, so if I said, here's an f function, here's a g function, what is f of g of 3? I might not want to go through what it is a second ago to just plug in. So what you could do is you could do this. So I'm going to take the g function and evaluate 3. Got to start on the inside. So I'm going to first find what g of 3 is. So g of 3 is 3 times, plug in the 3, minus 4. That's 9 minus 4. So g of 3 is 5. Okay, cool. Make that 5 a little bit neater. There we go. So g of 3 is 5. Well, now that I have that, I can figure out, separate kind of thought, this is not equal to the previous line, f of g of 3, and so I'm going to replace my x value in my f of x with what g of 3 equals. So this is going to be, this is basically the same thing as saying f of 5. I'm just evaluating this function at 5. What I just wrote wasn't completely necessary, but that might have been helpful. So instead of g of 3, that's just 5. So this is 5 times my 5. It just happened to be that same thing, 5 times 5, which is 25 plus 2. And notice we also get 27. So we get f of g of 3 is also 27, even if you do it that way. So to recap, I could, since I've already known what f of g of x is, I just take f of g of x, replace the x with the 3, simplify. Or, this is especially useful if I have not done what A and B was. I start on the inside, I find g of 3, and then I simplify, and I get down and I get 5. Then I take that g of 3 and I plug it into the f. So g of 3 is 5, and I simplify down. 5 times 5 is 2. Sorry, 5 times 5 is 25, plus 2 is the 27. So those are two methods to do the same thing. I would like you to pause the video and try this one on your own to do just the other way around, g of f of 3. All right, let's check our work. So we have, just a reminder, if you had figured out already in advance, which we did, was g of f of x was 15x plus 2. So g of f of 3 is 15 times 3 plus 2. So that's 45 plus 2, which is 47. Now you could do it the other way where you find f of 3, plug that into the g function, and then you will still get 47. All right, so let's move on and look at this. So I'm given two functions, this time s and l, where s is the square root function, so square root of x, and l is a linear function, x minus 2. Let's find s of L of x. So they don't have to just be two linear functions. They can be others. So let's do this. So if I'm going to do this, I'm going to find s of L of x. The L function, this L function, is going to be going inside of the f function, the s function. So I'm going to start with these square roots. So I start writing the s function until I hit my x. Oh, there's my x. Made it nice and long because I see what's coming. And then inside the x, inside the s function, instead of writing the x, I'm going to write the L function, but with the actual expression, so x minus 2. All right, then we simplify. That's it. There's nothing else to simplify. So it's square root of x minus 2. Just for notice, I do have this over here in gray. If you were to do that the other way around and put the s function inside the L function, it would be the square root of x and then just minus 2. So this is not the same thing. That order does matter. This is square root of x, the square root stops, and then we have a minus 2. So graphically, what's going on here? Well, we know transformations of functions. So this is the square root function shifted right 2. So I'm going to go to the right 2, put my little yellow plus that we did. Things just moved on me or something. Oh no, this is, let me just, sorry, a little pet peeve. I have this not in the right spot. Something happened weird. There we go. So I'm going to go right 2, put a plus, and then I'll graph, let's make it purple. So we'll graph our square root graph, but just starting at as if this is 0, 0. So as if this is 0, 0, there's 0, 0, 1, 1, 4, 1, 2, 3, 4, up 2. So I went 1, 2, 3, 4, up 2. And then do that again. 4, 5, 6, 7, 8, 9, up 1, 2, 3. So it's going to be here. You can, oh, I lost where it was. 1, 2, 2, 2. Notice a little tip. If I already counted over 4 to right here, and I now need to count 5, or sorry, now I need to count 9, I don't have to go back here and go 1, 2, 3, 4, 5, 6, 7, 8, 9. I already know this is 4, so just from here I go 4, 5, 6, 7, 8, 9. All right, so then we have that point at 11. The next one would be another 7 over, up another point about here-ish. So it's just aim in that direction. So swoop the square root, and like that. All right, so we know that because it's just to the right 2. This is an expectation. I can now take any two functions, plug them in. As long as it's in a form that's familiar to our transformations, you should then be able to graph it. So that's exciting. All right, so using what we know, maybe the graph, maybe something else, let's evaluate these things. So it says evaluate s of 2. So what is s of 2? Give you a second. All right, well, s of 2, that is not the function we see in B or A. That is one of the given functions. That is just s of 2, which is the square root of 2, which is, well, just that, square root of 2. I am not using this. All I'm using is just this statement right here. S of 2, well, just plug in a 2. And so just to be clear, that is would be on the s function, on the parent function of square root nonetheless, that is 2 comma square root of 2 on s of x. Now, this is what you might have been trying to do, s of L of 2. Now, this function would be helpful to label. This is s of L of x, which is the square root of x minus 2. This is why labels are helpful. So here, this is me plugging in a 2 and seeing what we get. So I can plug in into s of L of 2, which is the square root of x minus, let me just write it x first so I know what I'm plugging in, which is x minus 2. And then so to find s of L of 2, I'm going to plug in the square root of 2 minus 2, and we get square root of 0, which is just 0. So this is s of L of 2 is 0. How does that make sense on the graph? Well, that's that point right there. This is, that point is s of L of 2, which equals 0, or notice the point 2 comma 0 on my graph. That's 2 comma 0. All right. So let's do the domain and range for this. Now from our previous video, I could just take this square root of x minus 2 and do the domain. So let's do that. So I know that the s of L of x is square root of x minus 2. Red alert, red alert. And so that x minus 2 is inside of a square root. That's a problem. So we would say that that x minus 2 has to be greater than or equal to 0. So x has to be greater than or equal to 2. All right, so that's our domain. And look at the graph. Isn't that what we get on our graph? Yep, it can be 2 or bigger, which is exactly what we saw when we used our knowledge from the last video. So, or we can just be looking at the graph and do it. So the domain in set notation is x such that x is greater than or equal to 2, like I just wrote. Or if we were to do it in interval notation, it would be, and I'll use orange just so it's different. We are starting at 2, so square bracket to infinity, and that's it. For the range, we are going all the way down to 0, and then up forever. So in terms of set notation, this is the set of y such that y is greater than or equal to 0. In terms of interval notation, we are starting at 0, we're on 0. Make sure it's obvious that that's a square bracket, and then going on to infinity with a parenthesis. All right, so there's that one. So that's graphing composite functions. We're going to wrap up this video with more simplifying, but when they're not linear, and then we'll also in a second talk about solving. So we have d of x is x plus 1 over x minus 2, and q of x, which is 2x plus 1 over x minus 1. And I want to find out what is d of q of x. So this q function, or all of these x's, all of this, is going to go into that x, and it's also going to go into that x, right? So because we have two different x's, whatever's going in is going to go into both x's. Reminder, so if you saw like x squared plus x minus 9, I don't know, and I said evaluate, if I said to plug in 3 into each x, or whatever, so let's say this was f of x, and I said what is f of 3, right? This would be 3 squared plus 3 minus 9, right? Each of those x's would get the substitution. Same thing here, it's just not a number. Okay. So let's do this. So I'm going to color code again. Let me get my light blue back. So my d function is, this is d of, and it's q of x. move this down just a bit of a line, a few lines. There we go. I have the whole page for this one. You might need it. All right, so big fraction bar, and I'm going to go ahead and make it be nice and thick. And my x is going to be the 2x plus 1 over x minus 1. Make sure that your fraction bar, your big fraction bar, extends all the way to the left. And then just a plus 1. So what's left on my d function? Plus 1. And then my denominator, same thing. 2x plus 1 over x minus 1. And then the minus 2. So notice, if I was just to make this become an x, that's hard to see. If I was just to make that become an x and make this become an x, that's x plus 1, x minus 2, which is d. But this time, instead of x's, I'm writing the q function. All right, goody. Now we get to simplify. You might be thinking to yourself, Mr. Leach, you're evil. And be like, no, I'm generous. This is a prerequisite skill, and I'm wanting to review this prerequisite skill so that way you know how to do this before it becomes a bigger issue. So let's simplify this. So I have all these fractions inside a fraction. So working just in this numerator, oh, by the way, I'm going to do it's implied. It's like this implies that. It's literally like an equal sign with an arrow stuck on it, because I'm saying I'm going to go from this step to that way. If you work horizontally in your math, this is a good idea to use that. So I'm saying I'm going here, now I'm going over there. I prefer this instead of a single arrow. All right, so let's simplify. I need a common denominator. So to get a common denominator, keep having to switch colors. Let me keep that black. Let me switch back to, yeah. All right, so we're going to have any common denominator. So let me just copy this whole thing over. I know you can't do that, but oh well. Make this be a bit bigger. And then let's say my denominator over here in this numerator. So I'm just looking at the numerator. I'm not dealing with that denominator. My numerator is x minus, my denominator in my numerator, I know, is an x minus 1. This is just a 1. Its denominator is 1. So I just need to multiply by x minus 1 over x minus 1. All right, and I can do this because that's just 1. I can always multiply by 1 whenever I want. And then another x minus 1 over x minus 1 in the denominator, because the current denominator of this 2 is a 1. It needs to be an x minus 1. So I'm going to multiply by x minus 1. All right, so in my next line, I'm going to do that same thing. Equals, and I'm going to cheat again and just grab my previous line. So I now have an x minus 1 over x minus 1. When I distribute this 1, positive 1 times that, it's just x minus 1 over x minus 1. I'm going to go ahead and distribute this negative 2. So I'm going to actually write this as a plus, and then it's a negative 2x plus 2 over x minus 1. All right, because I took the negative as well and kind of sent it up. So I don't have to mess with that. My negative's already taken care of. It's been distributed into the numerator. All right. A little bit thicker there. There we go. Equal to, or implied big old fraction bar. And then now let me add up my numerator. So I'm going to have 2 thick, 2x plus 1 plus x minus 1. This is just this numerator right here, plus x minus 1. Now, if you're like, whoa, let me do a quick review. So let's say that I had, I'm just going to write this and then erase it, but if I had 2/3 plus 5/3, how would we add these fractions? Well, that's 2 plus the 5 over 3, right? The denominators don't change. Now, practically, if you're like, or that ends up being 7/3. This will be 7/3, right? you still don't believe me, just think pizza math. Okay? You have a pizza party, it's the end of the night, and you know how you always grab whatever's left over to try to shove them into as few boxes as possible. So I have a box that has one slice left, and they're cut into 8 pieces. One slice left. Then I have another box that has 3 slices left, and another box that has 2 slices left. How much of a pizza, total pizza, do we have? Well, that's 1 plus 3 plus 2, right? The denominator does not change. The denominator is the size of the slice, right? If I have halves, this is the size of the slice. If I have a quarter, this is the size of a slice. If I have an eighth, it's that big. If I have a 16th, it's that big. The denominator is the size of the slice. So this is 1 plus 3 is 4 plus 2 is 6. So you have 6/8 or 3/4 of a pizza remaining if this was your pizza party. So notice the denominator does not change when you add. Nothing about adding fractions changes once we add variables onto it. Okay? So I get a common denominator. Cool. Add it up. My numerators add, but I'm just putting together my denominator because that's your unit. Right? It's like saying I have 5 inches plus 3 inches. I now have 8 inches. It's not inches squared or any other things like that. All right, now in the denominator, it's going to be 2x plus 1 minus 2x plus 2 over the x minus 1. So a few things happening here. One, I have not done any, I've just put them together. My next step, I'm going to add, and then we do have these denominators to deal with. So what is 2x plus x on the top? That'll be 3x. 1 minus 1, that cancels rather to 0. So I'm left with, in my numerator, 3x over x minus 1. And then in the denominator, I have a 2x minus 2x. Those are going to cancel to 0, and a 1 plus 2 is 3. So that's 3 over x minus 1. Can make that prettier. Sure. Not really. All right. Okay. So few things that you can deal with dealing with this complex fraction. If you look at my fraction review, I've covered this. But you could write it this way. Actually, my personal preference, let me just show you what's actually easiest. Let me switch to purple again. Done with the colors. Let's make this be purple. All right. I'm going to multiply by x minus 1 secret over 1 over x minus 1 secret over 1 if you want that. Really, I'm just multiplying by x minus 1 over x minus 1. When I do, the x minus 1s are going to reduce from the top and the bottom, and we're left with 3x over 3. 3's reduce, left with x. That's the most efficient way to deal with this. Multiply by fancy 1. Notice x minus 1 over x minus 1 is just 1, so I can do that. I don't really need this over 1 business. Just multiplying by whatever is the common denominator of those two denominators, and then reduce. I did that in my fraction review video. You can take it in other steps. So 3x over x minus 1 divided by 3 over x minus 1. Dividing by a fraction is the same thing as multiplying by its reciprocal. 3x over x minus 1 times x minus 1 over 3. And here at this point, you'll see that the x minus 1's reduce. You might also be able to see right now that the 3's reduce, but we can get a 3x over 3. There we go, the 3's reduce, and we're left with just x. So either way you do it, you end up with x. So all of this is just x. Now, you might be staring at this video screen, yelling and cursing my name. You're like, Mr. effing Leach, you went from, we had this, and we went all through all this mess, and we got just x? Are you kidding me, Mr. Leach? All this for just x? No. If you watch, once you get to the very next video, you'll learn that this is a huge freaking deal. If you take two functions, you put one inside the other, and then the other inside of the other, and you end up with x, and that's it. This is a huge deal, but you got to watch the next video to see what that huge deal is. But this is a huge freaking deal. All right. So one more. This one will be faster, I promise. But it's slightly different because we have an equal sign. So it says solve d of j of x equals to 3. So I have the same d of x that we had a second ago, but this time I have a j of x. So let's solve this. Oh, let's find what d of j of x is. So to do this, I need a big fraction bar. Let me make it even thicker. Big fraction bar. Right? And then the j of x is inside the d. So x plus 5 inside that x plus 5 inside that x. And then we end up with x plus 5 plus 1. If you want to, you could throw parentheses around the x plus 5, but they're not really needed because there's no distribution. And then x plus 5 minus 2. And again, it's always a good idea to put parentheses around when you're substituting in, but there's no coefficient on that x, so there's no real need for that. All right. So then we end up with, don't forget, this is an equal sign, so equal 3. So I have an equation, now we need to solve for x. Let me first get like terms, or add like terms. So I'm going to have x plus 6 over x plus 3 equals 3. All right, I can't like reduce these x's. These don't reduce, those plus, that plus is a big old stop sign. I just need to get rid of the denominators. There's a classic trick whenever you're solving equations and you have variables in the denominator, and this really works if you just want to get rid of fractions and you just have numbers in the denominator. Multiply everything by the least common denominator. What's the denominator in this term? X plus 5. What's the denominator in this term? A 1. What's the least common multiple, least common denominator of x plus 3 and 1? X plus 3. So I'm going to multiply everything times x plus 3. So you get a, whoa, zooming in weird. You get a times x plus 3 over 1. And you get a times x plus 3 over 1. Everybody gets a times x plus 3 over 1. Be the Oprah of x plus 3s. So when I do that, the x plus 3s are on the left reduced to 1. And I now have an x plus 6. And then I distribute, but I'll just leave it like this. I'll distribute in the next step. But so just to be clear, what happened is these reduced, and then this over 1 is meaningless. I mean, it's just over 1, so it's not really anything. And I will distribute in this next step. So let's distribute. X plus 6 is 3x plus 9. And then I need to get my x's together, my numbers together. So I'm going to subtract the x, 1x from the left side, and end up with 2x on the right. Subtract the negative x from, minus x from both sides. X's cancel on the left, and I have a 2x on the right. Subtract 9 from both sides, and now I have a negative 3 on the left. Divide by 2, and I have a negative 3 halves is x. So if I take a negative 3 halves and plug it into here and here, I should end up with a positive 3. That's how you could check. All right, so composite functions open up a world of things to us. One, just in terms of simplifying, also at the end of the day, that's what a lot of our graphing things are. Plugging different functions in different orders, specifically really linear functions into different orders. And then we can deal with not just the linear functions, but rational functions, and then we can also solve them. So composite functions is another one of a powerful tool that basically at the end of the day is a substitution. Big powerful tool. Join me in the next video when I'll show and reveal what's so special about us getting in x. So I will see you then.